V naught plus whole square upon 2 Z naught, and reflected power will be equal to mode of gamma square into V naught plus whole square divided by 2 Z naught. So now if we consider the short circuited transmission line, so what will be the input impedance of the short circuited line? Z in for the short circuited line. So ZL is equal to 0. So if ZL is equal to 0, so from this equation, if ZL is equal to 0, Z in will be equal to J, Z naught and beta L for the lossless transmission line. So for the lossless transmission line, the short circuited input impedance will be equal to J, Z naught and beta L. Okay, what will be the reflection coefficient? So the reflection coefficient at the load will be equal to ZL minus Z naught divided by ZL plus Z naught. So ZL is 0 for short circuited line, so it will be minus 1. It will be equal to minus 1. So the reflection coefficient for the short circuited lossless transmission line is equal to minus. What will be the standing wave ratio? So what is the relationship between a standing wave ratio and reflection coefficient? S is equal to 1 plus mode of gamma divided by 1 minus mode of gamma. So that means 1 plus 1 divided by 1 minus 1. That will be infinity. So a standing wave ratio will be infinity for the short circuited lossless transmission. Okay, and ZSP is equal to J, Z naught and beta L. So it could be the input impedance, it could be capacitive or inductive. That will depend on the length of the transmission line. The electrical length beta. So theta, if theta is from 0 to pi by 2, so tan theta will be positive. So basically the input impedance will be inductive. If theta is from 90 degree to theta means beta into L. 90 to 180, so it will be capacitive. So that will depend on beta L, or you can say that will depend on the length of the transmission. So next we have the open circuited lossless transmission line. ZL tends to infinity. So ZL tends to infinity in this equation. If we put ZL tends to infinity, then what will happen? So it will be Z naught divided by 1 upon J tan beta L. Okay, if ZL tends to infinity. Because we can divide by ZL, so 1 plus, and that will be 0, and here 0 plus J tan beta L. Okay, so Z naught by J tan beta L. So minus J Z naught cos beta L. Minus J Z naught cos beta L, like this. So minus J Z naught cos beta L. Again, what will be the reflection coefficient at the load? ZL minus Z naught divided by Z plus Z naught. So ZL tends to infinity, so basically it will be 1. Reflection coefficient will be equal to 1. So what will be a standing wave ratio? 1 plus mode of gamma divided by 1 minus mode of gamma. So 1 plus 1 divided by 1 minus 1. So that will be basically infinity. So that means for the short circuited lossless transmission line, what was the input impedance? J Z naught and beta L. And what was the reflection coefficient? Minus 1, standing wave ratio. And for open circuited transmission line, for beta L, this will be equal to a standing wave ratio. Third case, we have meshed lossless transmission line. Then the transmission line is meshed. So basically, in that case, what will be the input impedance? If ZL is equal to Z0, what will be Z in? What will be Z in? If ZL is equal to Z0, what will be Z in? That is also equal to Z. And what will be the reflection coefficient? ZL minus Z0 divided by ZL plus Z0 to 0. So since this is a meshed lossless line, so because of matching there is no reflection. So the reflected voltage. So reflected voltage was V0 minus so reflected voltage V0 minus is equal to what will be the standing wave ratio? The standing wave ratio will be equal to 1. 1 plus mode of gamma will be 0 divided by 1 minus gamma. So it is 1. So basically, for the perfect matching of the transmission line, lossless line, we need a standing wave ratio as equal to 1. Okay. So this was the case for short circuited, open circuited and matched transmission line. So what is happening to the power? Transmitted power PT is equal to EI minus PR. So in this case, the meshed transmission line, V0 minus reflected voltage is equal to 0. What will be the reflected power? 0. So the complete incident power will be absorbed in the load. Okay, there is no reflection. There is no reflection from the load. And one more thing, what will be ZSC? This is ZSC and here ZOC. So what will be short circuited ZSC input impedance and open circuited input impedance of the transmission line? So what will be ZSC into ZOC? J Z0 tan beta L into minus J Z0 cos beta L. It will be equal to Z0 square. So three cases we have seen. Some other case we can discuss. Suppose the length of the transmission line is lambda by 2, half wavelength line lambda by 2. For this case, what will be the input impedance? What will be the input impedance? The input impedance will be equal to, you can calculate what was the formula for ZD. Zin is equal to Z0 into ZL plus J Z0 tan beta L divided by Z0 plus J ZL tan beta L. So what will be beta into L for lambda by 2 line? 2 pi by lambda into lambda by 2 pi. What will be tan 180 degree? 0. So basically Z in will be equal to ZL. So Z in will be equal to ZL. So if the length of the transmission line, if it is lambda by 2 long, and here we have ZL, so the input impedance is equal to ZL. So that means 1:1 transformation you can see. This ZL came here 1:1. There is no impedance transformation. That is the point. Okay, 1:1 transformation for the lambda by 2 length. So that means if we add lambda by 2 long length for the transmission line, the input impedance, so the load impedance will be same. That will be ZL. So impedance is not transformed, 1:1 transformation. Okay. If the length is equal to lambda by 4, then what is happening to the load impedance? What is ZL? If L is equal to lambda by 4. Again use this formula, tan beta into L. So now beta L will be equal to pi by 2. Tan pi by 2, you know, that is infinity. Tan pi by 2 is. So what will be ZL for this type of quarter wave transmission line, quarter wavelength line? So Zin will be equal to Z0 square divided by ZL. Z0 square divided by ZL. So now this load impedance is transformed. So now we are saying the input impedance for the quarter wavelength lambda by 4 transmission line as Z0 square by ZL. So that means what will be Z0? Z in into ZL under root, that will be Z. Characteristic impedance of the transmission line will be equal to root Z in into ZL. So that means suppose here we are having 50 ohm, or you keep 100 ohm. ZL is equal to 100 ohm, and we want to match this 100 ohm with 75 ohm. So what will be the characteristic impedance of this line? What we should choose? Z0 is equal to ZL into Zin. So we want to match 100 ohm with 75 ohm. So 75 into 100. This value we should take for Z0. Then it will be matched. And the length of the line will be, of course, lambda by. That you must remember for the quarter wave line. So we are using quarter wave line for matching the load impedance to the input impedance. Okay. So next we have lambda by 2 line. We have seen lambda by 4 line. Now let us discuss lambda by 8 transmission line. What is happening in this? If the length is equal to lambda by 8, then what will happen? If L is equal to lambda by 8, what will be beta into L? 2 pi by lambda into lambda by 8. So pi upon 4, pi by 4. What is tan pi by 4? Tan pi by 4 is equal to 1. So what will be the input impedance for this type of 1/8 wavelength transmission line? So the input impedance for this type of transmission line, now I have to clean it. To clean it, so what will be that basically? Z0 into ZL plus J Z0 divided by Z0 plus J ZL. So we have seen short circuited case, open circuited case, meshed line, lambda by 2 length line, lambda by 4 length line. Now if L is equal to lambda by, so what will be input impedance if the length of the transmission line is equal to lambda by 8? Here we have connected ZL. What will be input impedance? So Zn will be equal to, you know the formula for the lossless transmission line. If L is equal to lambda by 8, 1/8 wavelength transmission line, so it will be equal to Z0 to ZL plus J Z0 divided by Z0 plus J ZL. So what will be the magnitude of the input impedance? Yes, what will be the magnitude? That is equal to Z. That is equal to Z0. So for this type of transmission line, the Zin will be, of course, that is given here, but the magnitude of Zin, that will be always Z0. Okay, interesting or not? So 1/8 transmission line, and what was the case for lambda by 4? Zin is equal to Z0 square by ZL. And for lambda by 2, Zin is equal to ZL. For this case, Zin is equal to Z0. And for this case, you know already J Z0 tan beta L minus J Z0 what? This is the value of for short circuited. So now we will discuss and reflection coefficient, load reflection coefficient, gamma L, ZL. 1 second. ZL minus Z0. So ZL minus Z0 divided by, this we have done. And the standing wave ratio 1 plus mode of gamma divided by 1 minus. So next we will discuss Smith chart. We will start this new topic, Smith chart, and we'll see how we can use the Smith chart for matching the impedance from the load. So how we can use Smith chart in impedance transformation or impedance matching, for impedance matching purpose. So using single stub matching, we have single stub series matching, and shunt single stub matching, double stub matching we have. So now we will start Smith chart. And one more thing. Yes, so you can plot also, because you have this for short circuited line, you have ZSC is equal to J Z0 tan theta. Theta is equal to beta L. and ZOC is equal to minus J Z naught cot theta. Theta is equal to beta. So you can plot this with theta. Okay, theta is equal to beta here. 0 to theta you can say. So 0 to theta is pi by 2, theta is pi, theta is 3 pi by 2, and theta is 2 pi. So I told already that if the length is from 0 to pi by 2 as per the formula J Z naught and beta L, so it will be basically inductive. If it is 90 degree to 180 degree, it will be capacitive. Again inductive, then capacitive. This will repeat. And similarly for open circuited transmission line, minus J Z naught cos beta L. So minus J Z naught cos beta L. So if it is 0 to 90 degree, it will be capacitive. And then it is inductive, capacitive, inductive. That will depend on the electrical length or the length of the transmission line. So the input impedance of the short circuited and open circuited line can be plotted with electrical length of the transmission. Okay. Some questions are there that you can solve, no problem. I will start this Smith chart. So Smith chart, it is a graphical tool, graphical method of calculating the reflection coefficient, impedance on the transmission line, what is the input impedance, the standing wave ratio. So these things we can calculate using the Smith chart. We have analytical methods also using the mathematical expression formula we have, and this is a graphical technique. So this is simpler than the analytical method, but we have to. So Smith chart, what we are doing in Smith chart? This was proposed by Philip Smith. So the name Smith chart. So what we are doing on Smith chart and how we are basically constructing a Smith chart. So you can see one Smith chart here. So you can ask what is it? Basically, what is it? Smith chart. What it is showing. So basically it is showing you the intersection of the resistance circle with the reactance circle. Again the question will be what is resistance circle, what is reactance circle. So to understand that, you start from the reflection coefficient gamma is equal to Z minus Z naught divided by Z plus Z naught. Okay, start from here. So the reflection coefficient, load reflection coefficient will be equal to ZL, gamma L will be equal to ZL minus Z naught divided by Z plus Z. So the characteristic impedance of the transmission line can vary. It could be 50 ohm, it could be 75 ohm. So it could be 150 ohm, 100 ohm. So basically, we want to use one single Smith chart for all possible values of characteristic impedance. So what we will do? We will normalize all the impedances. All the impedances we will, input impedance, load impedance, characteristic impedance, everything. We will normalize with respect to the characteristic impedance of the transmission. So if we do that, what we will get? If we normalize all the impedance, see here, normalized load impedance will be equal to ZL divided by Z. So this we are saying real part plus J into imaginary part. So R is equal to real part of the normalized load impedance and X is the imaginary part of the normalized load impedance. And reflection coefficient is ZL minus Z naught divided by ZL plus Z naught. So that we can write as gamma R plus J, gamma I, real part of the reflection coefficient plus J into imaginary part of the reflection In polar form, we can write mode of gamma, angle of theta. So here we are seeing one circle. So on this unit circle, the Smith chart will be constructed. So on this unit circle, the mode of gamma is equal to 1. So when the mode of gamma is equal to 1, what that means, can you tell? Just now we were discussing mode of gamma is equal to 1. So what is the meaning of it? Mode of gamma is equal to 1. For the short circuited transmission line, what was the reflection coefficient? Minus. What will be mode of gamma? 1. For the open circuited transmission line, what will be mode of gamma? 1. So that means for the short circuited or for the open circuited transmission line, one thing is clear, mode of gamma will be equal to 1. So that means the short circuited and open circuited impedance should lie on this circle of unit length, because mode of gamma is basically showing here the radius. Are you getting it? So for this circle, mode of gamma is showing the radius. So if the radius is equal to 1 unit circle, so that means short circuited and open circuited impedance should lie so on the perimeter of this unit circle. We will see where will be short circuited impedance and open circuited impedance. For both the cases, mode of gamma is, and the standing wave ratio is also equal to infinity for both the cases. And when the mode of gamma is equal to 0, then what will happen? Mode of gamma is equal to 0, what that means? That means transmission line is meshed. Mode of gamma is equal to 0 means meshed transmission line, there is no reflection. So ZL is equal to Z0. So if ZL is equal to Z0, so mode of gamma will be equal to 0 and standing wave ratio will be equal to 1. So on the Smith chart, this point indicates meshed transmission line. Here the impedance, here the line is meshed. So this point signifies the meshed line. And what is the value of mode of gamma? It will vary from 0 to 1, including 0, including 1. So mode of gamma will vary from 0 to 1, including 0, including. It could be 0. I am talking about magnitude of gamma. Just be careful. It could be 0.5, 0.1, 0.9. Maximum it is 1. Okay. So and here what we are seeing, this is showing the angle of the reflection. In polar form we have magnitude and angle of the reflection. So this theta gamma is the angle from the real part of the reflection coefficient. Real in complex number, it is gamma r plus j into imaginary part of reflection. Gamma r plus j gamma I. So here this axis is showing the imaginary part of the reflection coefficient, and horizontal axis is showing the real part of the reflection. So horizontal axis is showing the real part of the reflection coefficient. What will be the reflection coefficient for the short circuited line? Gamma is equal to -1 for the short circuited, and for the open circuited, gamma is equal to 1. What will be gamma R and gamma I for the short circuited and open circuited case? What will be gamma R and gamma I? So for the short circuited, gamma R is equal to -1, gamma I is equal to 0. For the open circuited, gamma R is equal to 1, gamma I is equal to 0. Okay. So now can you tell where the short circuited impedance will lie? It will lie somewhere here, gamma R is equal to -1, and open circuited, gamma R is equal to 1, it will be here. So here this is open circuited and this is short circuited impedance. Okay. So we locate it. Okay, so next what we are doing here, I told you all the impedances will be normalized so that we can use one single Smith chart for all the characteristics, for the different characteristics. So gamma we can write like this, and this we can write ZL divided by Z naught because normalized. So ZL divided by Z naught is here. It is a small ZL. So a small ZL minus 1. A small ZL minus 1 because divided by Z naught. So divide by a small ZL plus 1. So normalized load impedance minus 1 divided by normalized load impedance plus 1. That is the reflection coefficient, which is equal to gamma R plus J gamma R. So this we have, and normalized ZL load impedance we can also write as R plus small r plus J small x. So small r is the real part of the normalized load impedance, and small x is the imaginary part of the normalized load. So basically this we have, this equation we have. There should not be any problem in this equation. We have basically gamma R plus J, gamma I is equal to ZL minus 1 divided by ZL plus 1. Okay. So from this equation, you can calculate ZL in terms of gamma R and gamma I. That is here. And ZL is R plus J. Okay. If you solve this equation, so from this equation you can the real and imaginary part you can separate of the load impedance normalized. So a small r and a small x you can write in terms of gamma R n. So that is here. A small r n. So this small r and a small x. So again if we rearrange these two equations, r and x, so we can write the same equation in this form. Gamma r minus r divided by 1 plus r whole square plus gamma I square is equal to 1 divided by 1 plus r whole square. So this is a locus of circle. So basically the circle of radius 1 upon 1 plus r and center at r divided by 1 plus r comma 0. This is known as the resistance circle. This circle is known as the resistance circle. And similarly you can write this also after rearranging. So here gamma r minus 1 whole square plus gamma I minus 1 by x whole square is equal to 1 by x whole square. So basically again, this is a equation of circle with center at 1 comma 1 by x, radius is equal to 1 upon x. So both the center and radius is dependent on the normalized reactance, load reactance. So it is known as the reactive circle, and it is known as the resistance circle, and reactance circle. Okay, so we have for the resistance circle we have center and radius. Center and radius, you know, radius is 1 upon 1 plus r, center, you know, r upon 1 plus r comma 0. For the reactance circle, we have radius 1 upon x and center is 1 upon 1 comma 1 upon x. Center is 1 comma 1 upon x. So next, can we plot resistance circle and reactance circle for different value of normalized load resistance and normalized load reactance? Can we plot it if the value of small r and small x is given? So that is plotted. For this value, if normalized resistance r is equal to 0, 1 upon 2, 1, 2, 5, infinity. Radius, you can calculate first radius and center, and then in MATLAB you can plot it. Okay. And if you plot it for these values of normalized load resistance, circle will be like this. This is your resistance circles for r is equal to 0.51, 2, 5, infinity. Yes. So this is your resistance circle. What you are seeing in this circle? If r is equal to 0, so we are here. R is equal to 0 for this circle. R is equal to. If r is equal to infinity, what will be the radius? 0. The radius will be 0 if r is equal to infinity. So radius will be 0 means very point circle. We have point circle. So circle will be a point for r is equal to infinity. We are here. It is a point circle. And this small circle is for r is equal to 5. This here for r is equal to 2, r equal to 1, r equal to 0.5. Okay. And gamma r is also equal to 0.5. For it is equal to 1. For it is equal to 2. R is equal to 5. Okay. So these are the circles for this. Here the horizontal axis is gamma r axis, and the vertical axis is gamma I axis. So r is equal to 0, r is equal to 0.5, r is equal to 1. So for this, can we calculate the reflection coefficient? If r is equal to 5 for this circle, if r is equal to 5, so what will be gamma r and gamma I? For calculating the reflection coefficient, we need both the real and imaginary part of the load impedance. Because what is gamma L? ZL minus 1 divided by ZL plus 1, where ZL is the normalized load impedance. So both r and x is basically required. Then we can calculate real and imaginary part of reflection coefficient. So only r, this will not give gamma r and gamma I. Okay, so now what about the reactance circle? The radius is 1 upon x. X is the normalized load impedance imaginary part. So normalized load reactance you can say. So and center is 1 comma 1 upon X. So again you take different value of normalized reactance. It is shown here. So if we take different value of normalized X reactance X 0 plus minus 1 y 2 plus minus 1 2 plus minus 2 because this is reactance, this is not resistance, so it could be plus minus capacitive reactance or inductive reactance plus minus 5 plus minus infinity 0 to plus minus infinity. What will be radius and center? First you calculate that for these values. So center, the x coordinate of the center is fixed at 1, the y coordinate is changing. Radius, when we are increasing the reactance, radius is decreasing. So we have calculated radius and center. Now we can plot the reactance circle. Here, this is typical example. For x is equal to 0 and plus minus 1 upon 2. For x is equal to, when x is equal to 0, what is the center and radius? Infinity and 1 comma infinity. So radius is infinity, center is 1 comma infinity. So x is equal to 0 is a line because the radius is infinity. It will be a line. So and okay, and if x is equal to 1 by 2 and minus 1 by 2. So first you see plus 1 by 2. So x is equal to 1 by 2 circle is here. So this circle will be like this, okay. So only inside this unit circle we have considered. So like this circle. And x is equal to minus 1 by 2. Then the circle will be below this. X is equal to below this gamma r x. Similarly, x is equal to 1 and x is equal to minus 1. Okay, and x is equal to 2 minus 2, 5 minus 5, and if x is infinity, then the radius is 0, point circle, and center is 1 comma 0. So center is 1 comma 0, 1 comma 0, and point circle, yes, is plus minus. So now if we superpose resistance circles and the reactance circles on the unit circle, so what will happen then? That will be your Smith chart. That will be your Smith chart. Here you have superposed. These are the resistance circle, you can see, and here this is the these are the reactance. So resistance circle and reactance. And one more type of circle you are seeing, that is constant a standing wave circle, because the standing wave ratio and reflection coefficient is related. So S is equal to 1 plus mode of gamma divided by 1 minus mode of gamma. So this is a standing wave ratio circle. So now suppose we want to locate some impedance on the Smith chart. So suppose we want to locate one impedance, normalized impedance, Z is equal to 2 plus J. How to locate Z is equal to 2 plus J? Where is that impedance on this chart? Z is equal to 2 plus J. So what is R and X or Z is equal to 2 plus J? R is equal to 2, X is equal to 1. So intersection of 2 plus J, R is equal to 2 circle and X is equal to 1 circle. So intersection of R is equal to 2 resistance circle and X is equal to 1 reactance circle. That point of intersection will give you normalized impedance 2 plus J. Where is that? R is equal to 2. Here it is written R is equal to 2.0. X is equal to 1 you want. So it is written here X is equal to 1. Take the intersection. Intersection is here. Here is your point 2 plus J. So you have located Z is equal to 2 plus J normalized. That point is here. This point will give you impedance 2 plus normalized. Okay. Now suppose you want to locate Z is equal to 1 minus J 0.5. How to locate? 1 minus J 0.5. R is equal to 1. X is equal to minus 0.5. Intersection of R is equal to 1 resistance circle and X is equal to minus 0.5 reactance circle. So R is equal to 1 and X is equal to minus 0.5. Check where is R is equal to 1. So R is equal to 1 is here. It is R is equal to 1. X is equal to minus 0.5. So see here, this is plus 0.5. It is minus 1.5. It is here. So here is your point. R is equal to 1.0. X is equal to minus 0.5. So here, this one. P2. This will give you normalized impedance to 1 minus J 0.5. R is equal to 1 and minus J 0.5. This is P2. So you have located 2 plus J and 1 minus J 0.5. Two impedances on this image chart. So similarly, you can locate normalized impedances on the image chart. Any normalized. Constant ascending wave ratio. So ascending wave, the value will vary from 1 to infinity. Ascending wave, it will vary from 1 including 1 to infinity. So S is equal to 1 circle, S is equal to 2 circle, S is equal to 3 circle, and so on. Here, this is S is equal to 1. Because when the line is matched, this point if you remember, here S will be equal to 1. So point circle, S is equal to 1. S is equal to 2. So here, are you seeing 2.0 is written here? 1.2, 1.4, 1.6, 1.8, 2.0. So basically, this circle will intersect the gamma R axis at which is S is equal to 2.0. So at 2.0, it is written here 2.0. So S is equal to 2.0. Now S is equal to 3. Again check here. Somewhere you will find 3.0. So that will be S is equal to 3. So center is here and radius. So like that you can draw the circle. So today we have seen the basics of and tomorrow we will continue the Smith chart. There are many properties of Smith chart. So tomorrow, day after tomorrow, next class we will continue Smith chart. Okay. If you have any question, you can ask.
No questions, sir.